A confidence score is useless until it changes behavior. Split conformal calibration turns held-out errors into an abstention threshold tied to a target risk. You'll implement split conformal calibration that fits an abstention threshold for a target error rate and returns a decision. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Large language models look precise on stage. In real-world use, they can also be confidently wrong, and that combination makes trusting the max probability risky for downstream users. Product teams usually want a simple rule: when to answer and when to abstain, plus a defensible statement about how often the accepted answers can be wrong. Conformal prediction gives us a distribution-free way to turn observed mistakes into a cutoff. The recipe is straightforward. Hold back a slice of labeled examples, see where the model slipped and how confident it was. Then choose a confidence threshold that keeps future accepted mistakes below the target rate. That threshold is useful because it's tied to held-out evidence, not guesswork. The trade-off is clear. You control a frequentist style event for the specific acceptance rule you deploy, so monitoring and periodic recalibration are still required as data or model behavior shifts. We'll build a compact pipeline, create a calibration split of model answers, compute a conformal cutoff for a target error rate, apply that cutoff to fresh eval items, and report a few simple metrics you can track. The code focuses on the core decision: accept when confidence exceeds the conformal threshold. Otherwise, abstain. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a held-out calibration set that pairs each answer's confidence with a ground truth correctness label, so the threshold has something real to learn from. This snippet creates the held-out evidence that calibration needs before any threshold is chosen. Raw confidence by itself is not enough, so each cal row pairs a confidence score with whether the answer was actually correct. The separate eval rows list is kept aside, so the threshold is not judged on the same examples used to set it. Observed errors gives a quick sanity check that the calibration split includes mistakes, because mistakes are the events the abstention rule must learn to avoid. The visible output shows the calibration size and error count, which anchors the rest of the workflow. We now need to turn those observed errors into a numeric cutoff that matches the product risk budget you want to control. This example turns observed held-out errors into a threshold instead of guessing one from intuition. The scores line assigns each wrong calibration answer its confidence and assigns correct answers 0, so a future accepted wrong answer corresponds to a score above the cutoff. Python standard library math.ceil implements the conservative split conformal rank using target error. Lowering target error usually pushes threshold higher, which means more abstentions and fewer accepted high-confidence mistakes. Raising it usually accepts more answers but permits more risk. The visible output is the calibrated answer threshold to reuse at serving or evaluation time. With a threshold in hand, we must apply it to unseen items and see how much traffic we would answer versus hold back. This code applies the calibrated rule to examples the threshold has not seen. Each row in decisions keeps the confidence, correctness label, and the Boolean answer decision from conf greater threshold. That makes the abstention policy explicit. Answers above the conformal cutoff are admitted, and the rest are held back. Answered, abstained, and answer rate are the first operational metrics an engineer usually wants when comparing prompt or model runs. The visible output shows the coverage of the policy over eval traffic, which matters because a safe threshold is only useful if it still answers enough requests. Sometimes, stakeholders want to compare different risk budgets to trade coverage for safety. We need a compact way to simulate that offline. This snippet shows why the target error rate is a product decision, not just a math constant. The cutoff function reuses Python standard library math.ceil to refit the conformal threshold for each candidate and targets. The last candidate is looser than the earlier baseline, so loose answered counts how many eval items would pass under that more permissive rule. This is not tuning on production truth. It is a compact offline comparison to make the abstention trade-off visible. The visible output shows how many extra answers the looser budget buys and the new threshold that caused the change. Finally, we want a short report that makes it easy to track changes across prompt templates or model versions. This code closes the loop with a small baseline report that can be tracked across prompt or model runs. The summarize function applies the same threshold, counts accepted answers, and separates two useful error views. All error is the rate of accepted wrong answers over all eval requests, which matches the conformal event being controlled. Selected error is the error rate among only the answers you chose to omit, which is often higher and should be tracked separately. The visible output gives a compact comparison-ready record, so future runs can be judged on both abstention volume and observed error behavior. If you map this toy pipeline to a production rollout, use a recent week of user queries for calibration and a different week for evaluation. Store the threshold with the model version. Then emit both answer rate and selected error to your monitoring dashboard, so changes in either metric trigger recalibration or a rollback. In short, split conformal calibration is a way to turn held-out mistakes into an abstention cutoff that matches a target risk. Use it when you need a defensible, data-driven rule to withhold uncertain LLM answers. Watch out, because it controls a specific acceptance event and still needs live monitoring for distribution shift. A practical next step is to tune target error on a labeled slice of your user logs and track selected error versus answer rate to find the right balance for your users. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.